The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the World Professional Automotive Community. Tom Forsyth is with us today. Please ask questions during the class by typing them into the questions area on your control panel. It's the little circle with a question mark on it. Tom will answer all of your questions at the conclusion of the presentation. Toward the end of the presentation, Tom will be discussing 5 test questions. And there is a PDF of these questions you can download from the handout section in your control panel. And the handout icon is underneath the question mark icon. It looks like a piece of paper with a little fold on the right top corner. So you can take notes on that for future reference as he discusses the specifics of and answers to each question. Also available for download is a PDF titled Fuel Trim Fault Conditions and Possible Causes. And Tom will be discussing that as well during the presentation. And be sure to check out the list of upcoming WTI classes that are available. And that, again, is in the handout section as well. So with that, we'll get right into it. Tom, thanks for being here. And I'm going to hand it over to you.
Thank you, Bruce. Hello, everybody. How you doing? Welcome to WorldPAC's lunchtime training class. And today's class is going to be on fuel trim diagnostic strategies. Let me shut my camera off so we can see the slide. Okay, so our objectives for today are to understand the difference between open loop and closed loop fuel control, understand and know the basic parameters required to enter into closed loop fuel control, understand the difference between short-term and long-term fuel trim control system, understand fuel trim behaviors and the differences between mass airflow and manifold absolute pressure systems, explain what fuel trim cells are, understand how to use fuel trim cells to diagnose different types of fuel control faults, understand how fuel trims can be skewed by many different types of engine performance faults, and use fuel trim to diagnose different types of engine performance faults. So let's get started. Fuel trim is a term that we use to describe fuel delivery. And basically what it is the PCM's adjustment of the injector pulse width to obtain the correct air-fuel ratio. The ideal air-fuel ratio is 14.7 to 1. That's 14.7 parts of air to 1 part of fuel. And we're trying to maintain this under most engine conditions to achieve the best emissions and best engine performance, and to allow for the catalytic converter to do its job correctly. Basic fuel injection pulse width. So we have something called a fuel map here, and each one of these fuel trim cells is showing you on the left-hand side what engine load was, and that's grams per second. And on the lower part, it's showing you engine RPM. So each one of these cells is showing you what typical injector duration or pulse width is while it's in that cell. Keep in mind that every manufacturer, these numbers may be a little bit different. They're not all the same. And even across different models within a manufacturer, these fuel trim cells may have a different amount of injector pulse width time for each cell. The fuel trim cell is basically going to be a non-volatile memory. The fuel trim cells will modify and adjust fuel injection pulse width depending upon what MAP or mass airflow is showing, engine coolant temp, intake air temp, barometric pressure, throttle position sensor, system voltage, and so on. So by adjusting the injector pulse width, we can adjust the amount of fuel that we're putting in the system to correct for either a lean or a rich condition. So right here, we're looking at 2 injector pulse widths. This is a scope pattern. And if you look at this red line right here, this section of the red line is at 12 volts. And right now the injector is off. When the computer gives the injector a ground, you'll see the voltage will go down to 0. This distance right here, while it's at 0, is the injector pulse width. That's the amount of time that the injector is on for. And that will change. If it needs to richen the mixture up, it will increase the amount of on time. If it needs to decrease the amount of fuel, it'll decrease the amount of on time. So the red line is showing an injector pulse width that is roughly 1.5 milliseconds, and the blue injector pulse width line is showing an injector pulse width that's roughly 0.75 milliseconds. And again, this changes dependent upon RPM, it changes dependent upon load, engine displacement. There's a lot of variables as to how long an injector will be turned on for, also the conditions that the engine is under. The two different types of loop statuses that we can have, we have open loop versus closed loop. Open loop is what happens right after you start the engine. When the engine's in closed loop, it's not using the oxygen sensor or air fuel ratio sensor to correct the air fuel mixture. It's strictly using engine load and RPM to determine what fuel trim cell it needs to be in. And then once it's in that fuel trim cell, it will then adjust the injector pulse width dependent upon what the other sensors are telling it. Things like the mass airflow sensor, MAP sensor, coolant sensor. So all those things will play a factor into what the computer does with the injector pulse width. Typically when it's at wide open throttle, we're going to see short-term fuel trim reading of 0. I have seen on some cars where if it idles for too long, it will go into open loop and the fuel trim will show 0 for short term. Closed loop is what happens after the engine started and the oxygen sensor or air fuel ratio sensor is heated up. They all have heaters in them now, and as it heats up, it'll start to produce a voltage. When it produces the right amount of voltage, the computer will then watch that sensor to determine what to do to adjust. Remember, the oxygen sensor and air fuel ratio sensor are measuring the oxygen content that's going into the exhaust from the combustion chamber. Once the PCM is in closed loop, it will watch what the oxygen sensor is doing and then make fine adjustments to the fuel trim mixture. There's two types of fuel trims that we deal with. One is called short-term fuel trim. The other one is called long-term fuel trim. And these two terms actually, out of everything terminology that we deal with in automotive, these terms actually make a lot of sense. Short-term fuel trim is basically an immediate response to what's going on. And a lot of it has to do with the oxygen sensor. The computer's watching the oxygen sensor. If the oxygen sensor is indicating that there's a lot of oxygen in the exhaust, which means a lean condition, the computer will then increase the injector pulse width to increase the amount of fuel that's entering into the engine. If there's too much or not enough oxygen in the exhaust, then the computer will do the opposite. It'll see that it's a rich condition. Low oxygen means rich condition. Then the computer will turn around and decrease the amount of fuel that enters into the combustion chamber. And this is, again, all to control what emission gases that the catalytic converter is controlling. So by controlling the oxygen content going into the catalytic converter can do its job much better. Short-term fuel trim calculations become active again after it goes into closed loop operation. And on most newer cars, like I said, they have heaters in these sensors and they can start operating within 10 seconds. Long-term fuel trim is basically over a long period of time, what has the computer had to do to maintain the correct air fuel ratio. Once it's in closed loop operation, the long-term fuel trim is a learned value that is based on short-term fuel trim corrections. When the vehicle reaches full operating temperature, the correction factors generated by the short-term fuel trim will actually store that information and be part of the long-term fuel trim cells. Long-term fuel trim corrections work much slower than short-term fuel trim. So if you see that short-term fuel trim is immediately responding to what the oxygen sensor or air fuel ratio sensor is doing. You'll notice that long-term fuel trim will take a lot longer to actually change those numbers. The idea behind long-term fuel trim is to try to keep short-term fuel trim as close to zero as possible. Ideal air fuel ratio for both long-term and short-term is 0. And typically I like to use the number 10%. Plus or minus 10% of adding or subtracting fuel is ideal for both short-term and long-term fuel trim. But again, long-term fuel trim's main goal is to try to keep short-term fuel trim as close to 0 as possible. So this right here is showing our fuel trim chart. And in the middle, we're looking at percentages at 0%. That's ideal. There's no corrections being made to long-term or short-term fuel trim. It's basically running at 14.7 to 1. If the computer needs to add fuel, which means goes positive, plus 10%, plus 20%, it's doing that to correct for a lean condition. And again, it's watching the oxygen sensor and air fuel ratio sensor to make this determination for short-term fuel trim. If the system is running too rich, then it will be subtracting fuel. So you'll see numbers fuel trim go negative. If you see a negative fuel trim, that means the computer is taking fuel away. If you see a positive fuel trim number like positive 20, then it is adding fuel to the system. Again, all to maintain an average of 14.7 to 1 air fuel ratio. Total fuel trim is actually a combination of short-term fuel trim and long-term fuel trim. This picture right here is showing fuel trim. At the top part of it, it's showing fuel trim data. This is live data that was going on with this vehicle at the time. You can see short-term fuel trim for both bank 1 and 2 are at 25%. Long-term fuel trim for bank 1 and 2 are at 61%. And that's immediately what was going on at the time. The total fuel trim average is the average over a period of time. And that's why, we say short-term and long-term added together is total fuel trim. And if you do the math here, you'll see that the total fuel trim that's being displayed at the bottom does not equate to what short-term and long-term is showing at the top, because what's being shown at the top is immediately, and what's being shown for the total fuel trim is the average over a period of time. So we have these fuel trim cells, and in this particular chart, they're showing 16 different cells. The computer's going to first look at engine load and engine RPM, and from that information, it's going to determine which fuel trim cell it needs to be in. At idle, it's going to be at the lower left. Low load, low RPM is going to be in the lower left, like cell 0. And if it's a high load, high RPM, then you're going to be up the top right, which is cell 15. Keep in mind that this is not the same for every manufacturer as far as the number of cells they have and what that cell value is. It's different from one manufacturer to another. And it's even different with the same manufacturer on different models. The numbers that are in the cells, the cell diagnostic weight, 22%, 67%, 11%, that has to do with the percentage that when the vehicle's testing a particular emission component or system for your IM flags, this happens to be the one for purge valve. For this particular manufacturer and make, 22% of the time that it's testing the purge valve on this car, it's going to be operating in cell 9. 67% when it's testing the purge valve, it's going to be in fuel trim cell number 5. And 11% of the time when it's testing the purge valve, it is going to be in cell 4. Every emission component and system is going to be tested in different fuel trim cells, and that's all calculated and figured out in the programming of the vehicle. This right here is showing the DRB3, which is Chrysler scan tool. The top half of this thing is showing live data as to what's going on with the vehicle. So these are our data pits for this particular vehicle. What I think is kind of neat about this is that the lower half of the screen is showing all the different fuel trim cells and what the fuel trim was doing at the time. 0 is no correction needed. If it's a positive, it's adding fuel. If it's a negative number, it's taking fuel away. So in this chart, you can see we have some that are positive. The cell that's highlighted, C24, is the current cell that it's in right now. So cell 24 is showing a positive of 33%, which means it's adding fuel for a lean condition. This is a Tech 2 screenshot. And this particular one is showing short-term fuel trim and long-term fuel trim on a Chevy Colorado. And the fuel trim cells that it operates again is going to be directly correlated between engine load and engine RPM. It doesn't show all the fuel trim cells at once. It just shows the current fuel trim cell that it's currently operating in. So in this case, you can see engine speeds at roughly 600, 700 RPM. Engine load is at 2%, and this it's currently running in fuel trim cell number 17. This particular car is idling in park. These next 3 screens are showing you similar things, but under different conditions. So the top screen is showing you basically 1100 RPM. Our engine load is at 5%, and right now we are operating in fuel trim cell number 5. The middle screen is showing you the engine RPM is at 2000 RPM. The engine load is at 19%, and the vehicle is operating in fuel trim cell number 9. And then the bottom screen is at 2700 RPMs. It has high engine load. You see throttle position angle is at 100%. So this is a wide open throttle stall test, and it is operating in fuel trim cell 13. Again, when a vehicle operates in different fuel trim cells, is different from one manufacturer to another. Just keep in mind the lower fuel trim cell numbers are typically for low RPM, low load, and the higher right-hand side fuel trim cells are for high RPM and high load. Fuel trim cells versus RPM and cell loads. On some vehicles, they will actually group fuel trim cells together. On this particular chart, they're showing that cell block number 1, which is at an idle speed. The vehicle's operating within this fuel trim cell, but if you get up at the higher right-hand side of this, all those green dots up to cell block 22, it's actually a combination of all those cells. So it's basically grouped cells together to control the air-fuel mixture. On this particular chart, this happens to be a BMW with an inline 3.0 liter engine. And I know most of you are probably familiar with Bank 1 and Bank 2 on V motors. And inline motors typically just have one bank. Well, on this motor, it's a 6-cylinder. It actually groups cylinders together. So the additional mixture adaptation is basically cylinders 1, 2, and 3. And the additional mixture adaptation 2 is for cylinders 4, 5, and 6. And then we have our grouped adaptation, again, cylinders 1, 2, and 3, and then our grouped adaptation 2, which is cylinders 4, 5, and 6. So I'm just trying to show you on this chart that even though it's an inline 6, we still may have grouped cylinders that they're using to control fuel mixture. This right here is showing you a similar thing, but this has to do with Volkswagen Audi. This is a VW with a V6. One of the kind of the cool things about this, and other scan tools do this, other manufacturers do this, but they do it pretty good as far as grouping these things. So you have 3 different groups that are being shown: Group 31, Group 32, and Group 33. And within each one of these groups, they'll actually group different data PIDs together. which makes it easier for you to diagnose. So in group 32, we have adaptation at idle for bank 1, sensor 1. We have adaptation for off idle or partial throttle for bank 1, sensor 1. And then we have adaptation idle for bank 2, sensor 1. And then adaptation partial, which is off idle for bank 2, sensor 1. So it's showing you a group of similar data PIDs all within that group. On here, we're looking at the Tech 2 screen, and this is a 2011 Cadillac. And on this, we're looking at the idle D cell fuel trim cells, and for bank 1 and bank 2. We're also looking at long-term fuel trim bank 1 and bank 2, and then the total fuel trim cells for bank 1 and 2. Again, just showing you different ways that a manufacturer will either group fuel trims together, give you total fuel trim, or give you individual short-term or long-term fuel trim. This is a really cool tool. If you've never got to use it, it's ATS eScan tool. It's got some really unique features that I've never seen on any other tool. This particular feature that we're showing you right now is pertaining to fuel trim, and this is what we call fuel trim mapping. And when we're doing fuel trim mapping, we can look at what the computer was doing to adjust the air fuel mixture or the fuel trim at all the different fuel trim cells. So we have all these blocks, all these different cells. On the left-hand side, they're showing throttle position. On the right-hand side, they're showing RPM. We drive the vehicle through all different loads and RPM and throttle position conditions, and it will tell us what fuel trims were for each one of these cells. In this particular case, we're looking at, if you see a green, that means that it's plus or minus 10%, and that's the ideal number. That's what we want to see. Other manufacturers, when they code or when they set a trouble code, or fuel trim trouble code is different from one manufacturer to another. I like to use the number 10% as an overall average. Some manufacturers, it may be less than that. I think Volkswagen has one that'll actually set a trouble code if fuel trim exceeds plus or minus 8%. There are other manufacturers where that number could be as high as 30%. But the general rule is I like to use is 10%. And again, we're trying to keep short term as close to zero as possible. And that's really the job of long term, is to try to get short term back into control. So in this particular car, we see that higher RPM, higher load, we're seeing fuel trim that is in control. If it's yellow, that means it's somewhere between 10 and 13%. Orange means that it's somewhere between 13 and 20%, so it's almost out of control. And then red means that it's plus or minus 20%, which is typically out of control. On this particular car, we can see that at idle or low load, low RPM, we're out of control. We're adding a lot of fuel. We're trying to correct for a problem. But at higher RPM and higher load, we are in control. On this car, the problem was there was a vacuum leak on a mass airflow sensor vehicle. And what happens with a vacuum leak is the computer's relying on the mass airflow sensor to tell it how much air is actually going into the engine so that it can put in the right amount of fuel. If there's a vacuum leak and the mass airflow sensor is not sensing that air that's able to get into the engine, it's telling the computer less air is going into the engine. Less air means less fuel. Less fuel means that the air fuel ratio sensor or the oxygen sensor is sensing a lean condition, so the computer will respond by adding more fuel. So that's why we're seeing these positive numbers in the red down at the lower left-hand side of the screen. The tool has the ability to show you long-term fuel trim, short-term fuel trim, total fuel trim, which is long-term and short-term. What you're looking at right here is long-term fuel trim. Again, keep in mind, fuel trim, you'd have to go out and drive this car under all conditions when you're doing long-term fuel trim because it reacts slow, but it's going to show you what the computer was trying to do to the injector pulse width under all load and RPM conditions. Here's another one. It's under heavy load, heavy RPM. You can see the computer's adding a lot of fuel. But under idle and low load, our fuel trims are green, and they're within that plus or minus 10%. So low RPM, low load, it's in control. Higher RPM, higher load, it's out of control. What was causing this on this particular car was a fuel volume issue. Either the vehicle has a fuel pump delivery problem, a restriction in the fuel system, a fuel volume problem, which typically isn't picked up at idle or low RPM. But when you get down the highway and you're on it and you need that extra fuel and the fuel system can't deliver it, that's what you're seeing right here. The fuel system could not deliver the amount of fuel that the engine needed. On this particular fuel trim map, you'll see that we have red across the map. So it's adding fuel across the map. Remember, all the examples I'm showing you, it's adding fuel, adding fuel. It can also be going the other way where it's subtracting fuel. So everything we're talking about so far has been an issue with a lean condition and the computer responding by adding more fuel. On this particular vehicle, 2005 Ford Ranger, we see that fuel trim values across the fuel trim map, it was adding fuel right across the map. So it was trying to add a lot of fuel, and it's adding a lot of fuel to correct for a extremely lean condition under all conditions. And again, this was another fuel delivery problem, an extreme delivery problem, a pump that wasn't producing the right amount of pressure or volume, injectors that weren't have the right flow rate and not allowing enough fuel to go through it. Here's another example of a freeze frame, or an example of a freeze frame record. This is a P0171. It was on a Colorado pickup. And you can see in here that the P0171, when it sets a freeze frame, it's telling you what was going on when the problem occurred. So when it sets the code, it takes a recording of what certain things were doing. So in this case, when the P0171 set, the engine load was at 3. It shows you that short-term fuel trim was 26%, long-term fuel trim was at 18%, and the engine speed was at 2100. Knowing engine load and engine speed or engine RPM is going to be critical to help you diagnose the problem. You want to verify the problem or verify the repair. You want to duplicate what the computer recorded when it set the code. So in this case, I find a problem, I fix the problem, I want to make sure it's okay. I'm going to drive the car so it has a 3% load and a 2100 RPM and see what the fuel trims do. So again, fuel trim is critical for diagnosing, freeze frame is critical for diagnosing fuel trim problems. Speed density versus mass airflow systems. Speed density system basically use a sensor that doesn't directly measure the amount of air entering the engine like a mass airflow. Basically, it's using vacuum to measure the load on the engine. And it's not just vacuum, it's using a couple of inputs. It'll monitor RPM, it'll monitor engine vacuum. When you have those two things together, they use what they call a speed density fuel calculation to control injector pulse width. The manifold vacuum or engine load input has the most authority when it's dealing with injector pulse width. Other sensors are also used to modify base injectors calculations or injector pulse width, things like the coolant sensor and the intake air temp sensor and so on. All those things together we call speed density equation. Here's an example of a speed density equation for a Chrysler. They look at RPM and they look at map sensor. And then from there, they have their basic calculations based on TPS, engine coolant temp, intake air temp. battery voltage, and long-term fuel trim. We have basically an O2 sensor or modifier that kind of fine tunes it. From there, we determine what short-term fuel trim and long-term fuel trim are going to do, and the end result is injector pulse width. Here's another example of that on another Chrysler. Same thing, we're looking at engine RPM and we're looking at map sensor. In this part, calculation of airflow, they also look at the EGR. Computer controls it, so it knows if the EGR is on and what it's doing to counter the change in map voltage that we would see when the EGR opens. Then we have our modifiers, again, your basic other sensors, TPS, engine coolant temp sense, intake air temp sensor, battery voltage. We have our feedback input, or fine tuning of the air fuel mixture from the front O2 sensor, or what they call the upstream O2 sensor. Then we have our adaptations or adaptives, short-term fuel trim, long-term fuel trim, and in this one they also include the purge vapor ratio, knowing if the purge valve is open or closed, they know is going to affect the amount of fuel mixture going into the engine. From there, they have the injector pulse width. TMAP on speed density systems, again, map sensor systems. Map sensors work a little bit slower as far as responding to changes in vacuum. So vehicles with speed density will calculate map based on inputs from throttle position, barometric pressure, idle air control if it has it. When they control the speed density on that, they call that TMAP. It's a model-based fuel strategy, and they calculate that value is called TMAP. Map sensors input validate this calculated value. Whenever map code is set and the computer can't use the map sensor information, then the PCM will strictly use the TMAP. Mass airflow sensors. Nice thing about mass airflow sensors, they directly give information to the computer as far as the amount of air that's entering into the engine, along with the temperature of the air for density. From that, the computer can directly correlate and figure out what injector pulse width should be. So between mass airflow sensor and engine RPM, those are the two inputs to compute basic injection duration, and then it would modify it dependent upon the other sensors, and then what the oxygen or air fuel ratio sensors are doing. Thing with mass airflow sensors, and when you're looking at a vehicle with a mass airflow sensor, general rule I like to use to figure out if a mass airflow sensor is telling the computer the right information is I like to see 1 liter equals 1 gram per second. So if I have a 3-liter engine, I want to see a minimum of 3 grams per second of air going into that engine. And this is going to be at idle with a hot engine. Normal operating temperature at idle, the liter should equal the 1 gram per second for every liter. If you're dealing with a 4-liter engine, you're going to see 4 grams per second. Other things to know about fuel correction and modifications. Obviously, oxygen sensors and air fuel ratio sensors are going to basically be like the fine tuning of the vehicle. So everything else that we talked about as far as the sensor input information, coolant sensor, throttle position, that's all pre-combustion. The oxygen sensor and air fuel ratio sensors, that's post-combustion. So the computer's going to look at that and say, all right, how did I do with my injector pulse width controlling the air fuel mixture? And the oxygen sensor is going to basically let it know how it did. So if there's a lot of oxygen in the exhaust, it knows that it's a lean condition and it's going to richen it up. If there's little oxygen in the exhaust, a rich condition, it's going to lean it out. So it'll look at oxygen sensors and air fuel ratio sensors, look at long-term fuel trim and short-term fuel trim and our other sensors to determine what injector pulse width is going to be. Freeze frame data, as I said before, it's very valuable to help you determine exactly what was going on when the code set, whether it's a PO 171, 172, 173, 174, whatever the fuel trim code is, monitoring the freeze frame data or looking at the freeze frame data that the PCM has stored is going to help you to duplicate that condition. Here's some examples of freeze frame. This is a 2008 Toyota RAV4 with a 2.4 liter engine. It set a PO 171. When that set, the calculated load was at 28%. Short-term fuel trim was 20%. Long-term fuel trim was 21%. Engine RPM was 872 RPMs. So in this case, we're dealing with a vehicle that is running lean. The computer is adding fuel because you see those positive numbers for short-term and long-term fuel trim. By using the calculated load and the engine RPM, I can duplicate that condition and see what the fuel trims are doing. Keep in mind, long-term fuel trim takes a while to change in responses, not like short-term. Short-term is basically immediately changes depending on the conditions. Here's another example, 2010 Cadillac CTS. Short-term was at 24. Long-term was at 37. Again, both positive, so both adding a lot of fuel. The RPM was at 1,000. Load isn't being shown on this particular screen. It's a data PID that's somewhere else on the screen. But knowing the load and the RPM can help me to duplicate that condition. Reset and fuel trim. What reset and fuel trim means is that you're going to take no matter what the fuel trims are right now, and you're going to bring them back to zero. There are two ways of doing that. The first way is to use a scan tool. They have something called fuel trim adaptation or fuel trim reset. And what that'll do is no matter what the fuel trims are, through the scan tool, you can actually tell it to reset and it'll put everything back to zero. I've done this on some cars to actually verify that there's a problem. So fuel trim's either positive or negative. It doesn't matter which way, but if it's positive or negative, I will hit the fuel trim reset, which will bring it back to zero, and then I'll watch short-term and long-term, but again, short-term is going to react quicker to see which direction it goes. If the car come in with fuel trims that were negative and I reset it back to zero and they immediately go back to negative, then I know I'm dealing with an actual problem. The other way of setting fuel trim adaptations is by letting the computer do it. And that's really the preferred method of doing it. So you have a car that either has positive or negative fuel trims. You figure out what's wrong with it. You find a problem. You fix the problem. You want to see if the computer's happy with your fix. Then you go out and drive it and you watch fuel trims. If the fuel trims were both positive, and then you see now short-term fuel trim is negative and long-term fuel trim is positive, but the total fuel trim is, again, plus or minus 10%, then you know the vehicle's going back to being in control. So here's an example of that. Vehicle had an issue, fixed the vehicle. Short-term fuel trim immediately responded by going -10. Long-term fuel trim was 15. Our total fuel trim would be +5. +5 is plus or minus 10% of where we need to be. So this vehicle is going back to zero, where we want to be. These are the charts that Bruce was talking about that are in the handout section on the control panel. And again, these are just generic charts. Not every car, not every manufacturer is the same, but it's a good starting point. There are 3 columns. First column is, what is the fuel trim doing? Is it adding fuel? Is it taking fuel away? Is the fuel normal? Is it not adding or subtracting fuel? The second column is showing you the condition, the RPM and the load. And then the last column is telling you likely causes of the fault. So the first First row, adding fuel at low speeds, low load on a mass airflow system vehicle, it's probably going to be a vacuum leak. You have unmeasured air getting into the engine that the mass airflow sensor is not seeing, very much like the example I showed you on the fuel trim map. Adding fuel at high speeds and high load on a mass airflow or a MAP sensor vehicle, we're probably dealing with low fuel delivery, low pressure, or low volume. If we're adding fuel under all conditions on a mass airflow sensor vehicle, we may have unmeasured air or leaks, or possibly a contaminated mass airflow sensor, or low fuel volume or delivery, like the example I showed you with the fuel trim map. On MAP sensor vehicles, under calculating load under all conditions, that could be a MAP sensor problem or a vacuum line for the MAP sensor. Subtracting fuel at low speeds and low loads. A mass airflow or MAP sensor vehicle, fuel injector or fuel pressure regulator leak, it's taking fuel away, so it's obviously it's trying to compensate for a rich condition. So if we have too much fuel getting in or an injector leaking, we're going to see it's subtracting fuel. Subtracting fuel under a high speed and high load on MAP vehicles, MAPs, again, MAP sensor hose issue, or possibly a restricted exhaust or mechanical fault. Subtracting fuel under all conditions on a mass airflow or a MAP vehicle could be one of our data input faults, looking at your sensors. And I can't stress this enough, when you're dealing with fuel trim problems, you don't want to just look at air fuel ratio sensors or oxygen sensors. You don't want to just look at mass airflow or MAP sensors. You really need to look at all your input sensors. I had a car a few weeks ago, and it was adding a lot of fuel. Customer's complaint was a hard start. It would crank for a long time, and he could smell fuel. I connected it up. It did have a check engine light. The customer didn't care about that, but it had a fuel trim code, and it was a rich mixture. And when I looked at the data pads, the coolant sensor was reading minus 40 degrees, which I can't believe it didn't throw a code for that. It should have thrown a code, but it didn't. So it was showing minus 40 degrees. The computer thought that it was extremely cold out, so it was dumping in a lot of fuel. Fixed the coolant sensor circuit problem, and my fuel trims went back to normal, plus the check engine light was out, and more importantly, the customer was happy because his vehicle started right away. More fuel trim conditions and possible faults. If you have one bank that is positive and one bank is negative under all load and RPM conditions, you're probably dealing with an exhaust gas sensor issue. Possibly the connectors are swapped or something like that. If you're dealing with one bank being positive and one bank being negative, and it's more severe at high speeds and high loads, you're probably dealing with a restricted exhaust. And typically when you're dealing, we call that an imbalance. When you have an imbalance from bank to bank on fuel trims, typically whichever bank is negative is gonna be the side that has the restricted exhaust. So once you know that, then you can start running your other tests, maybe doing an exhaust back pressure test. Some of the engines that now have some type of a tune-in valve built into the intake to change it from a single plane to dual plane intake. You may look at that. I had a Ford V motor that had this system that was using one solenoid to control both of these valves in the intake, and one of the on one valve it actually broke the linkage, so the cylinder had an imbalance from side to side. One bank being positive, one bank being normal under all conditions. Probably looking at an exhaust gas sensor calibration issue, possibly an air injection fault, exhaust leak ahead of the upstream O2 sensor or the front O2 sensor, maybe a misfire that's causing a lean shift on the exhaust gas oxygen sensor for that bank. Remember, when you have a misfire, if it's a misfire that causes a skip, not only are you not burning fuel, but you're not using oxygen. And air fuel ratio sensors and oxygen sensors, all they sense are oxygen. So you have a skip, whether it's a misfire or a lean skip, for whatever reason, you're going to be dumping in not only fuel, but you'll be dumping in oxygen too. And the computer's going to see that, see all the oxygen, and what it's going to do is it's going to start adding more fuel, even though it doesn't need it. If you have one bank that's negative and one bank that's normal under all conditions, looking at your exhaust gas oxygen sensors to see if there's an issue with them and they're not working correct. These last two have to do with turbocharged or supercharged engines. If you are adding fuel, or if you're adding fuel and it's at low speed, low load, or you're subtracting fuel at high speed, high load, and it's a mass airflow sensor vehicle, you want to check for air leaks between the turbochargers or supercharger and the throttle plate. So the question is the engine in fuel control? And I said before, what's going to cause a vehicle set of code for fuel trim is going to be different from one manufacturer to another, but here's some general things that you can look at. In this case, long-term fuel trims are high. If short-term fuel trim values are reasonable, the vehicle is in fuel control. Again, we want that short-term fuel trim to be as close to zero as possible. So if I saw a short-term fuel trim that was like +5 or -5, and my long-term fuel trim was, +15 or -15, I wouldn't necessarily say that the vehicle fuel control was out of control. So in this example on the chart, it's showing short-term fuel trim and long-term fuel trim are relatively high. Long-term fuel trims are approximately 30%. Short-term fuel trims are +13% and +16%. What's more important is the exhaust gas oxygen sensor or air fuel ratio sensor. Sensors are showing, the upstream sensor is showing that they are responding to short-term fuel trim commands. If that's the case, then the engine is in control, or the computer's in control, fuel control. On this particular one, it's a Tech 2. And even though long-term fuel trim and total fuel trim numbers are normal, short-term fuel trim, bank 1 and bank 2, are maxed out at +25%. And again, short-term fuel trim, immediate response to what's going on. We want that as close to zero as possible. This engine is not in control, even though the long-term fuel trims aren't too bad. It's the short terms that we're concerned about. Barometric pressure and the effects that barometric pressure has on fuel trims. PCM needs to know what the altitude is that the engine's operating in. It needs to know changes in barometric pressure in order to adjust the injector pulse width to make sure it has the correct fuel calculation. Different manufacturers use different units of measurement for barometric pressure. I know, there are some KPA, HPA, so on and so on. And depending on the car and the manufacturer you're working on, you may be dealing with a manufacturer or a barometric pressure that's giving you the unit measurement in something that you might not understand. There are calculators out there. ALLDATA has them, Mitchell has them. You can just Google it. A barometric pressure of this KPA, what would that equal, in millibars, or what would that equal in PSI? Again, it's easy information to find out. Just keep in mind, not every manufacturer is using the same scale or the same unit of measurement. In this case right here, we're looking at barometric pressure effects on fuel trim. This is the same vehicle, both these charts. It's a 2010 F-150. The upper chart is showing you the barometric pressure at sea level is 158 Hertz. That's normal fuel. That's normal barometric pressure at sea level. So the fuel trims are normal. The lower chart is showing you the barometric sensor value at 11,000 feet is 128. Again, the fuel trims are normal. When you're looking at fuel trims and you see that fuel trims are out, you want to look at barometric pressure and you want to determine is that vehicle operating or does the computer think that it's operating at the right altitude? So here's another one. This is using the Ford scan tool, 2005 Ford Ranger. The engine shows that the data was taken at sea level, but the fuel trims are abnormal. The barometric pressure at sea level should be 158. The scan tool is showing approximately 130 hertz. And that's the correct for 7,000 foot altitude, not at sea level altitude. So in this case, you can see that the fuel trims, the computer's modifying the fuel trims to correct for what it thinks the barometric pressure is. This right here is a DBR3 Chrysler scan tool showing barometric pressure data for a Chrysler Sebring, and the barometric pressure is showing 30 inches of Hg, and that would be normal for barometric pressure at sea level. Again, different manufacturers are going to display this, use different units of measurement for barometric pressure. So we have a case study with a Chrysler Sebring, came from another shop. They attempted to make the repairs. They did a tune-up on it. The customer's complaint was the check engine light was on. It had a P0171 lean bank 1, a P0174 lean bank 2. The other shop replaced the fuel pump. They also replaced the fuel injectors. The DRB scan tool showed that there was still codes in it, a 171 and a 174. Looking at the data PIDs for the scan tool, for the 171 and 174, you can see that cell 24, remember on a Chrysler DRB3, they're giving you the cell map down at the bottom, and the top half is what's actually going on for the data PIDs. So the fuel trim cell for cell 24 was plus 33%, so it's adding 33% more fuel to correct for a problem. We hitched up the ATS scan tool and we did a fuel trim map to it to see what was going on. And you can see the lower numbers, it was adding a lot of fuel, but at a higher load and higher RPM, it was okay. Looking at more information, looking at the data PIDs, key on, engine off, the map sensor PID value showed 91 kPa. With the key on, engine off, 91 kPa equals 26 inches of Hg, which is not the right altitude. This vehicle was at sea level, and it didn't think it was at sea level because of the barometric pressure. This is that conversion calculator that I told you about that you can get on ALLDATA or Mitchell. You guys have probably used that before. If you don't, again, if you don't understand what the manufacturer is showing you for the unit of measurement they're using, a calculator like this can be very helpful. Hitched up a vacuum to measure engine vacuum. Engine vacuum was good. The map sensor was good too. What was kind of interesting about this particular vehicle is the barometric pressure reading it gets from the map sensor. So key on, engine off, the barometric pressure was showing that it was at a higher altitude than it really was. Once the engine was running, the map sensor was showing that it was working correctly. It was showing the correct engine vacuum. So the repair, replace a faulty map sensor. We put in a new map sensor, and then once we changed the map sensor, we went through, did a fuel trim map again with the ATS tool. Everything looked good, everything was in control. Looked at the data PIDs, and you can see now the data PID for the map sensor was 101 kPa with the key on, engine off. That's normal. 101, 102 kPa is sea level for barometric pressure. And then we look at with the DRB3, we start looking at those fuel trim cells, and we see that the current fuel trim cell that it's operating in, cell C25 was +2, And for C25 on the other bank was +3. C24, which was the cell it was operating in when we first looked at it, and those numbers were crazy high, 33%. Now they're +7 and +6. So problem fixed. Okay, we got some quick repair questions, and I know Bruce said that these questions were all in the handout section, so if you wanted to download them, you could. I'm going to go through them. So technician A states fuel trim cells are based on engine RPM and load. Technician B states that fuel trim cells contain short-term fuel trim adjustments. Who is correct? So the best answer here is going to be A. Fuel trim cells are basically engine RPM and load, and it's long-term. On a V8 engine, has a 171 lean bank 1 and a 173 ridge code on bank 2. Observing the fuel trims, we see that bank 1 has a +40. We see that bank 2 has a -38. Which answer is the most probable cause? And the best answer for here is going to be bank 2 has a clogged catalytic converter. Remember, when you're dealing with an imbalance on a V motor like this, an extreme imbalance, +40, -38, that's pretty extreme. The side that has the negative fuel trim is going to be the side that has the restricted catalytic converter, or possibly a restricted intake for bank 2, whether it was that tune-in valve or something like that. Review question 4, cylinder turbocharged engine has a 171 system 2 lean and a 172 fuel system 2 rich. Those are set in the engine controller. Engine idles poorly and has low power. Which answers below is the most probable cause? Choose one. And the best answer here would be a torn intake boot between the turbo and the throttle plate. Review question number 4. 4-cylinder engines in closed loop at idle in park will observe in the scan tool data short-term fuel trim is at -15 and long-term fuel trim is at +20. Technician A states adaptive fuel trim has not been cleared after correcting a vacuum leak. Technician B states that total fuel trim is +5. Who is correct? Best answer there would be both of them. Review question 5. 5-liter engine has a 171 fuel system lean bank 1 and a 174 fuel system lean bank 2. The engine's hot at idle in park. Observing the scan tool data, the mass airflow sensor is 4 grams per second. Fuel trims on both banks are adding fuel. The vehicle is driven under wide open throttle and the calculated load data PID is at 60%. Which answer below is the most probable cause? And the best answer here is bad mass airflow sensor. If the answer there was a vacuum leak before the mass airflow sensor, then we could go that route too, but that wasn't one of the possible answers. So that's my presentation.
All right, Tom, thank you.
You're welcome.
Got a couple of questions. We're almost at our top of the hour, so here we go. Does the 1 gram per liter rate rule apply to turbo engines?
No, it does not. That's when you start getting into turbo engines and you start talking about volumetric efficiency and things like that, and the amount of air going into an engine. Turbochargers and superchargers is going to affect that. Typically, when you're talking about volumetric efficiency and the amount of air and the amount of engine's ability to breathe, because that's really what it is, typical naturally aspirated engines will have anywhere from 80 to 100% volumetric efficiency, whereas a turbocharged and supercharged engine could be up to 130%. If you stick to that rule where it's idle, hot, and in park, and the turbocharger and supercharger is not, obviously working, it'll be close to that. It'll be close to the 1 gram per liter.
Okay, thanks. Can you use fuel trims to diagnose EGR or purge valve problems?
So, so on older cars, possibly. On newer cars, the computer knows if the EGR is open because the computer's controlling it. Most of them have feedback sensors, so it knows, and it's going to adjust and adapt what fuel trims are doing when it knows the EGR is on. And again, I said if when you're dealing with fuel trim problems, if there are any other codes stored in the module, you want to go after those codes first. The only time you're dealing strictly with fuel trim is when fuel trims are the only codes that are set. So good question.
Okay, and we got one more. What would fuel trim look like if you had a leaking fuel injector?
So you got a leaking fuel injector. It depends on the level of the leak. If it's leaking enough where it's causing a misfire, then the computer is going to, again, misfire is going to interpret that as too much oxygen. It's even going to add more fuel. If it's just creating a little bit of a rich condition, then it's going to do the opposite. You're going to see that it's, because it's a rich condition, it's going to take fuel away. It depends on the level of leak, really, what it comes down to.
All right, well, that is going to wrap it up for today. Thank you, Tom, for being here. Appreciate it. And thanks everyone else for being here today. If you have any further questions about today's class, send an email. It's wti@worldpac.com. And be sure to include the class number in the subject line. Today's class is LTT 432. And lastly, and importantly, take a few minutes to fill out our survey. We're scheduling classes for 2024, and we look at your comments and suggestions, and it really helps us make sure we're providing you with the training that you need and you want. And with that, any final thoughts, Tom?
I just want to thank everybody for attending today's lesson, and I really hope you got something out of it. Every class that I've ever attended, if I learn one thing, I'm happy. So hopefully you learned something from this and it helps you do your job and be able to fix these problem cars.
Awesome. Thanks again, Tom. And I know everyone has busy schedules, so appreciate you tuning in here and being with us today. The webinar is now ending, but we hope you can join us again for another one real soon. Take care. Thanks, everyone.
Bye, Bruce.